from Holomorphic Chern-Simons theory. Please, Tian, go ahead.
Okay, thank you. Thank you, organizer, for organizing this so wonderful school and the conferences. Also appreciate for giving me this opportunity to speak here to discuss with you guys about my recent work in collaboration with Peking and IGFAE. And now I'm in KITS. I have moved from Peking University to KITS UCAS. Okay. Yeah, I hope everybody can read my slides. Kind of a little small. I try to do better. Okay. So the question I want to ask, or the question I'm interested in, is that what are integral systems? It turns out it's not a simple question. And I found an answer actually from the book by Hitchin. His answer is that the question can occupy a whole book or be dismissed as, if you're going to ask, you'll never know. So basically, it seems that integral system is very complicated and very fruitful and broad. There's no simple questions to cover all the aspects of integrability. We do have some guidelines. These 3 guidelines are also from this book. Actually, it's kind of a combination of lecture notes. The title of the book is Integral System, Twistor, Loop Groups, and Riemann Surfaces. In the book, Hitchin gives 3 main guidelines in his time, I think. The first 2 are very obvious. The first one is that the system should have many conserved quantities. And the second one is that the system should be solved explicitly. That kind of our orientation about how integral systems look like. The third one kind of not that simple to understand, but he said the pseudo equations of algebra geometry. So this third one kind of subtle. It cannot be explained in a simple word, I think. So after maybe 20 years study, probably you can add more guidelines into this list. Okay. So given the breadth of this integrability, it would be nice for us to have a systematic framework just to organize all the possible, all the integral system we have known. But the first systematic framework I know or I encounter is called this Daharsabel construction. I find this construction actually from this book, Introduction to Classical Integral Systems by Barbellum, Bannard, and Tian. I just find this construction is very nice and powerful and beautiful. But unfortunately, this construction is not discussed too much in recent literature, as far as I know. The construction is very clear, actually. It's very simple. The only input is the Lux equation, or the Lux equation, or the Lux matrix. Given this Lux matrix, there's a systematic way to construct integrable systems, in particular, classical mechanical system. Basically, the basic idea is that by studying the analytic structure of this Lux matrix, we can specify different integral models. So here, the lambda is the spectral parameter, and we assume in the Lux matrix, they can have poles in the complex plane. By the way, this spectral parameter take values in the whole complex plane. So we can expand the Lux matrices L and M into this Lorentz series. And in a compact way, basically, I label the singular part with LK, means it's a singular part at the pole of lambda K. It's similar for MK. And it turns out around each pole, say lambda K, this LK and MK can be diagonalized in the same time with the same regular similar transformation, like this. Here, this AK and the BK are diagonal matrices under some assumption. Basically, you assume all the eigenvalues of LK and MK are different, so can do this diagonalization. After this transformation, I find the last equation is equivalent to this one, very simple one. From this one, we find the eigenvalue of the L is conserved, and this MK actually is determined by this L. So only in the L, we do not need M. So here I give a summary about ingredients of this construction. In this construction, the dynamical variables are just the matrix elements of the singular part because M is determined by L. And the model is specified by the number and the order of the poles of the Lux matrix. And by choosing the polynomials, the special polynomials, basically we choose different dynamical flows. For example, here, you can define a Hamiltonian as a trace of the nth power of L. There's also corresponding L matrix. But until now, it seems that we already have a complete integral system, but there's no physics yet. We only have some mathematics conclusions because we start from equation. So right now we only have equations. We do not have a theory yet. To really have a classical system, we also need to specify what's the simplex structure. That's where physics comes in. It's kind of also tricky here. To see the complex structure, we need to look at this equation again. From this equation, the last matrix can be interpreted as belonging to the core joint orbit. This is crucial, under the loop group G. After this interpretation, we know there's a natural Poisson bracket on this core joint orbit. It's called the constant Krylov Poisson bracket. Through this one, we can really define the simplex structure of this whole of this integral system. The reason I introduce or describe this construction is because later on I will reveal some other constructions. It's kind of related to this one. The basic idea is the same. Only this part is different. Only the last part is different. The first three are very similar. But there's also an analog of this Zarohov subset construction for field theory. But again, unfortunately, it's less discussed. It's less studied. Probably one reason is that, again, the input is just the equation. So the output is also some equations, or the equation motion or the Lux equation. So it's very hard to identify what the theory is, what the theory you construct really is. For example, if you do not know what's the Lagrangian or action of the theory correspond to. So maybe there's a more efficient framework to do this job. So that comes to the second framework I want to introduce, the Foliage Chern-Simons theory. Probably everybody in this room know this theory because this is a topic of the summer school. So I assume this theory is well introduced. It was introduced by Cosello, Witten, and Yamazaki in this in the series of works. And later on, it's studied in very, very detail and extended by this Deldak, Lacroix, Macro, and Vesido in this book, in this paper called DMMV. Right now, we really have a physical starting point. We start from a physical theory. It's a 4D Chern-Simons theory. I'll just briefly review the theory because later on I'll use some of the conclusion of this theory, of this construction. Here, the total dimension of time is 4. So it's decomposing into a physical spacetime, maybe in Euclidean signature or linear signature, and a projective spacetime. Here, this omega, the meromorphic one form on the CP1. And the CSA just a standard Chern-Simons Lagrangian density. But A is a partial connection. You see here, it doesn't have this AZ component. For my convenience, I also introduced the complex coordinate on this physical spacetime. Sorry, I used W kind of confused with omega, but this is the W's. And there's a very simple relation between the Skates connection with the Lux connection in the 2D theory you will construct. It turns out they are related by this, again, by the similar transformation. I call it similar transformation. But now this G hat or this transformation parameter is a smooth function on the whole spacetime for both the sigma and the CP1. Now we see some similar structure now. For example, the zeros, there's some zeros in this one form. So if there are zeros, which means this action is kind of degenerate. So to kill this problem, we should introduce poles to this gate connection. And we need to specify the property of this pole. So this is also called disordered defects by Yamazaki and Cosello. And then the equation motion of this gate field naturally becomes the flux condition of this last connection. Not all of them, one of them, there are in total 3 equation motions. One of them will naturally become this. But I'll have more. For these two, kind of similar to the previous Daharsabel subset construction, but we now have some new things. First, we also have some poles in this one form. This poles will serve as some boundaries for this gauge field. So the gauge field not only have poles, but also have boundaries. And to have well-defined the variational principle, we need to specify boundary conditions. It's right some right here. So if we choose a proper boundary condition, you will find the action actually is localized on the poles of the one form. So actually this action is really two-dimensional. So the upshot of the construction is that choosing this one form and the boundary condition amount to specify a model. Okay. So let's talk more about the boundary conditions. The boundary conditions are studied in this paper. And for simplicity, let's just assume the one form omega at most has double poles. For higher poles, we have the reference here. They really studied higher poles situation. So at the double pole, we don't have double pole or single pole. Double poles, we can choose this Dirichlet boundary condition. We just fix the value of connection at the boundary to be 0. So if you look back to this boundary condition, actually there's only one equation. It's a sum of something equal to 0. There's only one equation. But most of the time, we need to require its term, the term and its pole one is separately. So actually, we have several different equations. But single poles actually come in pair. Even diamond poles is there itself, but single poles come in pair. For example, a pair of single pole, this boundary equations look like this one. Then you can choose this omega, choose the parameters in this one form to set the radial opposite. Then we can rewrite this boundary condition as an inner product of some Lie algebra. Actually, it's a double copy of the original gauge algebra. So this condition just make sure this inner product is standard. So now we can solve the boundary condition in another way. We just assume this pair actually belongs to a Lagrangian subalgebra. Then the inner product is 0. In other words, this double copy delta and this L actually is a Manning pair. Actually, we can actually rewrite the first condition also as a Manning pair, like this one. We just add this derivative. Then okay, so just put the boundary condition in the same form. So this analysis means the boundary conditions are actually classified by Manning pair. Okay, so if we choose the Manning pair as our boundary condition, we will find we have some freedom to choose the G hat. The G hat has some gauge freedoms. Because if you look at final 2D action, it depends on this G at its pole. This archipelago condition means we can choose a gauge such that the G hat are more or less localized at its poles. But that's not the end. Even though we have this nice 2D form, there's still some gauge transformation, some gauge freedoms. There are two types. First, remember the relation between the gauge connection and the Lux connection is through this similar transformation. But for the L, it only has space-time components, but no z-bar components. So this means the AZ bar is simply looks like a pure gauge in the form of pure gauge. If there's some ambiguity, you can right multiply some field on this G hat. But the G hat is supported on the physical space-time. So I would call this gauge transformation a global gauge transformation because it doesn't depend on the CP1. So I just call it global transformation. It acts on all the poles in the same way. There's another kind of maybe called a local gauge transformation given by this left multiplication. But now this U will depend on the position in the projected space. So that's why I call it local system. But after you do this gate estimation, you also change modify the gate connection. But we have to fix the boundary condition for this gate connection. So this U should not violate this boundary condition. That means if you do not impose boundary conditions, this U will be in the whole gate group. But after you impose boundary conditions, the gate symmetry is restricted by the boundary condition. Okay, there's a basic ingredient of this framework. And now I'll give you two standard or very classic examples of these constructions. The first one is this Flexor model with this West-Germinal term. It's one form it's like this. It has 2 zeros and 2 double poles. So as I said before, at the 2 double poles, I will use this differentiate boundary conditions. Now we have 2 double poles. So in principle, we should have 2 GX. One is a G at the 0, the other one is a G at the infinity. But I can use this global gate transformation to set one of them to be identity. Since this A is fixed to be 0, there'll be no more local gate transformations. So this one already fixed all the gate freedoms. Then you substitute this G and the A into the result into this one. You find the final action just is a Flexor model with a West-Germinal term. So the second example is called the Young-Baxter signal model or Lambda deformation. To construct this model and to split one double pole into single poles. So now we have 2 zeros, 1 double pole, and 2 single poles. At the double pole, I still impose this differentiated boundary condition. So there's no local gate freedom there. At the single poles, I choose a special main pair or a special Lagrangian subalgebra. There's kind of a quick summary about this algebra. Actually, it's classified or described by this as R matrix. This R minus 1, this R plus 1. This R satisfies this modified classical Young-Baxter equation. So for one solution of this modified classical equation, I can define this Lagrangian subalgebra. And it turns out this double copy of algebra and this GR and the G delta, each main triple. G delta defined like this. So just 2 elements should be the same. Main triple means this pair, this 2 is a main pair. This 2 is another main pair. So if you choose GR, you will get a Young-Baxter model. If you choose G delta, you will get the Lambda deformation. Similarly, I can use a global gate symmetry to set this G at infinity to be identity. Then add the 2 single poles because now the gate symmetry is this GR. So the residual gate freedom is G times G modulo this GR. Because G delta is complementary to G delta or to GR, so we can fix this G to be like this. Basically, the take value in this G delta. Then you follow standard procedure, you will find the resulting model is really the Young-Baxter model and the Lambda deformation. Okay. This is the second framework I introduced. The third one is called Antiseptic Young or Antiseptic Young equations. A standard textbook about this formalism is by Mason and Woodhouse. I'll just explain this formalism very briefly. For example, let's consider a 4-dimensional system with a flat metric in this form, where TU, VW are computing a complex coordinates. Then we also consider a connection on a bundle with covariant derivative like this. Then we can write this antiseptic Young equations in a very compact way, actually in a single equations like this. But Z is also, again, a free spectral parameter. It already looks very similar to a flat condition of Lux connections. So to develop or to obtain integrable systems, we need to do something called the dimensional reduction. Basically, we assume there's some isometries in this theory, or there's some isometries in this background. Then by modulo those isometries, the subgroup of the isometries, we can obtain 1D, 2D, or 3D integrable theories. Well, there's some examples. But this formalism is well studied in the 90s. But again, right now, it's a kind of, there are not too many works about this formalism anymore. There's some examples which can be constructed from this formalism. One is the total field equations, the KdV equations, and this nonlinear Schrodinger equations. I list these two examples because these three theories have not been constructed from this previous 4D Chern-Simons theory. But maybe it seems like these two formalisms are kind of disjoint, or they don't fully overlap. But there's a geometric interpretation about this antiseptic Young theory. I'm sorry, by the antiseptic Young equations. But by the Penrose word transformation, the antiseptic Young connections can be identified with the holomorphic vector bundles on the twistor space. So one may imagine or conjecture, which is a natural expectation, this antiseptic Young equation is equivalent to some holomorphic Chern-Simons on twistor space. Again, they're kind of similar, this antiseptic Young equation kind of like the kind of higher dimensional version of the Cherenkov Sabbat construction. We do not have a theory. We do not have a physical theory input. We only have some equations. So if you input some equation, what you can get only equations. You cannot get the Lagrangian or the theory directly. So if we have this kind of formalism, we kind of in the same footing as the Fourier Chern-Simons theory. We can start from physical theory and to derive a physical theory. But before that, I want to just give a brief summary about the twistor notations. They put everybody on the same page. So the twistor space of the complexified spacetime, or this maybe four-dimensional complex spacetime, is the CP3 modular CP1. So on the CP3, we can introduce a homogeneous coordinates with G alpha. There'll be four components, but we can regroup this four component into spinors. And this removed CP1 is characterized by this omega A0. So if we fix the Euclidean signature, the spinor conjugation is given by this particular one. It's not the normal complex conjugation. For example, if you conjugate again, you get minus itself. Then we can think there's a fibration about this twistor space. For each point in the twistor space, we can project to this we can project to the point in the Euclidean 4D Euclidean space through this projection. Because we want to have a holomorphic theory, so we need to distinguish holomorphic part and anti-holomorphic part. So we can define the 1-0 forms, which are the basis of the anti-holomorphic part, like this. So by doing the conjugation, we get this holomorphic basis, or the 1-0 forms. Here, I also use the standard notations of spinor calculus. Okay. But this theory is 6-dimensional, and is proposed by Costello and the Peterson and Skinner. So this is the action. It looks very similar to the previous 4D Chern-Simons action. Instead of one form, now we have a 3 form. So omega is 3-0 form. Here, phi is like a twist function. Basically, it contains the information of 0 or poles. And again, this one is standard Chern-Simons Lagrangian density. And this A bar is the kind of partial connection. Partial means, by partial, I mean it doesn't have the holomorphic part, holomorphic component. So in Skinner's paper, they choose a very special, or in Costello or Skinner's original arguments, they choose a very special 3 forms, 0 forms. If you choose this one, you can prove, or they proved really, the previous 4D Chern-Simons action actually can be derived from this 60 holomorphic Chern-Simons theory by a symmetry reduction. Well, how the whole diagram can go along this way. So first we get this by do the symmetry reduction to obtain this 4D Chern-Simons theory, and just as before we look at the pole and the zeros to get a 2D theory. But this procedure they call it solving over fiber or solving along fibers. Alternatively, we can switch out the two operations. Because in the omega, we also have poles and zeros. So we can perform a similar operations or solving along fibers to get some 4D integrable theories. In this special case, this 4D theory will be a 4D Westermann-Newton model. After that, we do this symmetry reduction to get final 2D theory. In this simple example, this diagram is commutative. So the two ways are equivalent. The two ways are equivalent. But in our work, we try to generalize this diagram to other theories, which are also suggested by Peterson and Skinner. But we find sometimes this diagram is not commutative. Okay. Let's just work out this example in details. This good example. I mean, everything works. This diagram is really commutative. Let's work out this example in details. But first, I go along the left route, meaning we do the symmetry reduction first and the solving along fiber. To do symmetry reduction, we need to choose a 2D because in the end we want to have a 4D theory. So we want to choose a 2D group, symmetry group. The group we choose is generated by two null translations, which can be written like this. The assumed symmetries means this gate connection, the lead derivative as a gate connection vanishes. So this is my assumption of to do symmetry reduction. And it turns out there's a better way to do the reduction. We can contract this Lagrange density by the bivector. These two vectors I chose for the reduction. You just contract your Lagrange density with this bivector. You can get this reduced Lagrange density. Indeed, it's the 4D Chern-Simons theory. During the contraction, you will find this one form is related to, yes, this one form is given by this one. This phi is the phi in the straight form. But now we have two more zeros. Another connection relation is that the 4D gate. I just start from here, but probably. So there are two routes to construct the 2D theory. Once you perform the symmetry reduction first to get this 4D Chern-Simons theory, then you do just as a standard solving along fibers, or you can solve along fiber first, since the omega itself has poles and zeros. But then you can use a similar procedure to obtain a 4D theory, and then after you have the 4D theory, you do some symmetry reduction to get final 2D theories. Okay, so first let's go along the left route. Let's do a symmetry reduction. So to do symmetry reduction, you choose a 2D symmetry group. Here I choose the 2D group to be generated by two null translations, which I introduced here. Now I need to assume the last connection. So the gate connection should have such a symmetries. Meaning the lead derivative of this gate connection should vanish. So to do this symmetry reduction, we can just contract this Lagrange density with this bivectors directly. Then you will get a 4D Lagrange density. And you can check, indeed, it's the same one as the 4D Chern-Simons theory. Then you can have the relations between the one form and the straight form. It turns out it's given by the same twist function, but with two more zeros. And also a relation between this 4-dimensional gate connection with this 60 gate connections. These are very complicated expressions. Here I introduce two more vector fields like this. Okay, if you simplify this equation a little bit, we will find these two equations, which we call the matching conditions. Basically, if you assume the diagram, the whole diagram is commutative, you should have these identifications, probably up to some gate transformation. This matching condition is important because we need to use this one to help us to choose boundary conditions if we try to do the solving over fiber here to the 60 theory directly. Okay. So now the procedure is similar because this one form has two double poles and two simple zeros. Double poles, I can just choose the same tertiary boundary conditions and use a global gate transformations. We can set one of the sigma tilde. The sigma tilde is paired with G hat. The same thing. We can set one of them to be identity. Then these two just rewrite your boundary conditions with the Lux connections. So you can solve these two equations in this way. In the end, I got this this action of the 2D theory. Indeed, is this principal Chern model with a West-Hamilton term, where the level is given by this expression. Okay, so far so good. Let's go along the right route. Let's do the sum over fiber first. But from 60 to 40. We can choose boundary condition by looking at the matching condition. The matching condition suggests I should have imposed these boundary conditions. And this actually there are 4 equations, which implies basically this A hat is 0. Or we can look at the boundary equation motions coming from the variations. It's like this, very long. But you can see pretty much similar, it's same as the previous 4D theory. In 4D theory, you have a very similar boundary equation motions. And it tells you as a double pole, you can choose directional boundary conditions. So these two approach are equivalent in this case. The other thing are the same. I still have 2 double poles, so I can choose my gates like this. Skip this part. In the end, you really got a 4D theory like this, and it coincides with the 4D Western-Witten model. So on top of this one, you can do the further symmetry reduction on the same 2D symmetry group. It's along the same directions back here. I need to do some pullback from the twistor space to this Euclidean spacetime, but the vector field actually look similar. For convenience, and introduces 4 vector fields. So I've skipped all the details, but in the end, you find this 2D theory is same as the previous one. It's the principal Chern model with the measurement term. Now it's very instructive to derive the 2D Lux connection directly from this Antiseptic Young equations. Without going along this procedure, we just derive the 2D Lux connection directly. So this is Antiseptic Young equations. In the first step, if I solve over fiber, I will get some expression for this 4D gate connections. This one is fixed by my boundary conditions. Then I substitute this result into my Antiseptic Young equations. I get this one. Actually, there are 3 equations in total. Since alpha beta is not 0, the inner product of alpha is not 0, I can choose alpha and beta as a tilde, then project this whole equation into 3 equations. So the projections. So now I can do the second step to do the symmetry reductions. Indeed, the second one, after symmetry reduction, it indeed gives this flatness condition of this current as expected. And this third one gives you this equation motion of the theory. So far so good. So so from this one, we can extract a Lux connection by contracting this gate field with the spectral combinations. And theta will be my spectral parameter. So everything matched nicely. So next, we try to generalize this story to other integral models as suggested by Bittelshen and Skinner. Our first sample is a Lambda deformation. So the left route is very straightforward. If I do symmetry reduction, I just get this 4D Chern-Simons theory with this new one form. You have 1 double pole, 2 simple poles, and 2 simple zeros. These 2 simple zeros come from the symmetry reduction on the other side. So from this form, I can identify the 3-0 form. So it should be like this. And this is standard form of the standard form of this one form for you to derive Lambda deformation. And also, I want to impose this condition to make sure the two residues are opposite. So we can have a standard algebra structure. So I can impose these boundary conditions as before. And the double poles, I still use the Dirichlet boundary condition. For the G hat, first I use the global gauge transformation to fix this, the double pole, the field double pole to be identity, and I use the relative gauge transformation to fix one of the G tilde to be identity. So now, let's say the situation is same as before, you can derive this 2D Lambda deformations. Now let's try another route. Let's solve along fiber first, and then do the symmetry reduction. From the matching condition, I get a boundary condition like this one. Indeed, this boundary condition solve the boundary equation of motions. But the problem is that given this boundary condition, it means these two pairs are not in this Lagrangian subalgebra. These two things are in conflict. So we encounter a problem. So even though the matching condition provides us the right boundary conditions, we solve the boundary equation motions, but there's no good algebraic structure anymore, such that the residual gauge freedoms in the 2D action can be removed. So basically it means it's not clear how to choose this G tilde anymore, such that all the gauge symmetries are fixed, just because this boundary conditions does not give me a good algebraic structure. So the one possible solution, the solution we can come up with is that we can discard the matching condition. Just assume the diagram is not commutative, so we can discard the matching condition, but impose this correct boundary condition directly. Let's see what's the result. So this is the 4D action and the 2D action we got. We have this connected term. We also have this virtual term. They took the same form, actually, the same form as the lambda deformed models, but with some constraint. The lambda parameter must be fixed to be plus minus 1. This is a by sign, because that's the limit of the parameter, that's the limit of the lambda in this deformed model. In particular, sometimes if lambda to be 1, this operator is not invertible. So kind of this model is bad behaved. Now we now have some comments why we have such situation. Why we have to fix these lambda values. Where artificially or officially we find there's no enough parameters in this tree form. We don't have enough parameters to this tree form, such that we can end up with some free parameters. And the other hint is that there's no zeros. We only have poles in this tree form, but there's no zeros. It means actually we are not inserting any defects in the sense of Cosello and Yamazaki's. The zeros in this one form actually come from the symmetry reduction. So this kind of observation suggests us we need to consider more complicated tree form to obtain some interesting theory.
Yeah, we lost you.
Okay, I will pick up what I stopped last time. So last time I stopped here where I talk about this Lambda deformation. And if you go along the left route, if you do the symmetry reduction first to get a 4D model and do the solve along fiber to get 2D theory, indeed you can get 2D Lambda deformed model. However, if you do the solve of fiber first and do the symmetry reduction, you get this 4D model and 2D model. They look like the Lambda deformed model, but with the free parameter actually fixed to be plus minus 1. Which is the limit of this parameter. This is kind of is bad because when lambda is 1, this operator may not be invertible. So their theory are not well defined. So now let's have some comments why we have this constraint. One of the constraints, the hint is that actually there are no enough parameters in the original 3 form, such that we can end up with a free parameter
the other hint is that actually there is no zeros at all in the 3 form. This means actually we are not inserting any defects. The zeros in the 1 form come from the procedure of symmetry reduction. So it suggests if we want to construct the physical integral models, we need to consider more complicated 3 forms. So before that, let's consider another simple model, the Young-Baxter model, to see what happens. Again, we'll meet the same problem with the matching condition is incomplete with the boundary conditions. So I have to impose this boundary condition directly. The left will give you the same result, but if we do the solve along fiber first, indeed we end up with 2D action like this, with a free parameter eta. But it's nothing like a Young-Baxter model. Actually, it belongs to a class of models discussed in this paper. And they have shown this model is integrable only when eta picks some specific values. So this example suggests if you start from 60 holomorphic Chern-Simons at 3 space and do the solve along fiber and the symmetry reduction, you may not get the 2D integral models in general. That's very out of intuition because each step seems to be innocent. We have not do anything break the integrability. So what happens? To understand the failure of this construction, let's just contract these antiseptic Young equations with some spinors. Here I choose the star to be beta and beta hat. As before, I get 3 equations. Solving on fiber basically fix this 4D gauge connection to some form with the boundary conditions. That's how I end up with this and this. Then I perform a symmetry reduction. Again, the third one reduces to the equation motion of this 2D theory. And the second one reduces to a flattest condition, surprisingly. The problem is that this flattest condition is not equivalent to the flattest condition of JW as required by this theory. They are consistent only when you fix this parameter to some particular value. Okay, then we just move on to consider more complicated 3 forms. First, we just split the other double pole into simple poles and impose these 2 boundary conditions. So if you solve along fiber first, you get the 2D theory, which looks like this Lambda Young-Baxter model. We're supposed to have 2 free parameters, but in this construction, you only have 1 free parameter. As before, we miss one of the free parameters. And the second example is that we consider a fourth order pole. And as a cost, we have to add 2 zeros. Now we have 2 more free parameters. But at the fourth pole, because the fourth pole will have to give more information or informations to describe the fourth pole. And the boundary conditions like this one, we have to impose one to make sure the action is well behaved. Otherwise, the action is divergent. By treating this condition, we can have well behaved action. Just because we have more, we need to support more information on this fourth pole, and not all the gate freedom can be fixed. In order to, apart from the degree freedom described by Lambda deformation, we have some field theory left over with coupled with this Lambda model. So again, it's a very complicated model, and we have not recognized anything familiar in the literature. It probably is a new integral model, but it's very complicated. Okay, in the third example, we add another double pole, also 2 zeros. Add 2 double poles, we impose the threshold boundary condition. Simple again, I impose this this simple condition before. So we go along the left route, meaning we do the symmetry reduction first to get Foliage Chern-Simons theory and solve along fiber. It has been shown in this paper the resulting 2D theory is the Young-Baxter deformed model, but in the so-called trigonometric description. Basically, go along this route, you will get the Young-Baxter model. However, if you solve along fiber first and do the symmetry reduction, you get a very complicated 2D theories. It's nothing like Young-Baxter model. Presumably, it's not integrable. We made some mistakes in our previous calculations, but now we're trying to fix that. But definitely, it's not Young-Baxter model for sure. Okay, here is the conclusion. It was proposed that from a 2D holomorphic Chern-Simons on twist space, we have two different routes to construct 2D integral models. One route is that you do the symmetry reduction first to get a Foliage Chern-Simons theory and insert defects of solve-along fiber to get the 2D integral models. Alternatively, you can insert defects of solve-along fiber first to get a 4D model and do the symmetry reduction to get a 2D theory. Our results show this diagram's not always commutative. In particular, the red route sometimes is problematic. But now we have not found the general rule when the red route is problematic. I will leave that in the future study. Okay, thanks.